Hello. Goal of today's video lesson is to explore simplification of rational expressions. It's important that you understand what we're doing because simplify is the one major important thing. Is this is not an equation, this is an expression, and expressions can't be solved because we have nothing for this expression to equal. It's not a complete sentence, as it were. So the only thing we do with expressions is we try to make them as simple as possible. And so something that we've learned in the past is simplification of these kinds of expressions. First of all, we remember, I hope, that we can divide and multiply in any order we want. So instead of multiplying the a's and b's on the top and multiplying the a's and b's on the bottom, I separate, and so I divide the a's from the a's, and I divide the b's from the b's separately, and then I multiply the results. So this is a recollection of the old quotient rule, which says you can subtract the exponents when you divide numbers of the same bases. Remember, the subtraction of exponents is simply dividing out common factors. One of the a factors in the numerator divides to 1 when it's divided by one of the a's in the denominator, leaving us with 2 extra a factors in the numerator. Here there's one b factor and 2 b factors in the denominator. One of those is going to divide out with the other and leaving you with a b value that's supposed to be in the denominator. This is stuff that we've worked on. It's just a quick review. But what I'd like to do is to show you how we can make use of structure, and I'll explain what I mean in just one second. Here is another exercise, and it looks to the untrained eye as if this is way more complicated, way more challenging than the exercise that we previously completed. And the reason is because in the mind of the untrained mathematician, the quantity x minus 2 in parentheses is seen as if it is 2 separate numbers. They're not treated as a singular entity. But the reality is these grouping symbols or parentheses, they force the x minus 2 to get gelled together as one single quantity. In other words, I could take all of this stuff and just call it a, for example. Every time I see an x minus 2, I could just replace it with the number a. It looks nicer, but it means the same thing, see? But really, if you look at this long enough, you'd say, hey, this is a cubed over a times b over b squared. It's just that the a's and b's are written as more complicated quantities, but they are still treated the same way. The value of x minus 2 is the same as the value of x minus 2. 2x plus 5 is the same as 2x plus 5, just as b is the same as b and a is the same as a. So in order to simplify this expression, I have to do the exact same kind of thinking that I just did a moment ago. They have the same basis, so you could subtract the exponents, divide out common factors, as it were, and basically rewrite everything. So what I did here is I took one of these 2x plus 5s, divided it with one of those, and there was one left over in the denominator. I took 3 of these x minus 2s, divided one of those x minus 2s out, leaving us with 2 extras in the numerator. We'll talk about how to check this momentarily. But now get to the next issue. First of all, I will point out that this is what we call algebraic structure. You see, the structure of this exercise is exactly the same as the structure of this exercise. Cubed times over times squared. That's just whatever is. As long as they're the same, we can follow the same rules. We get to our third example, and this is by far, to an untrained eye, something that's just virtually impossible. I think there's a lot of students who'd be like, I have no idea where to start. And what they might try to do is to like cancel numbers out. You know, here's a 4 and here's a 4, and you cross them out. But that's not doing real math. That's just pray and wish and hope you get right. But let's try to be a little bit more sophisticated about this. There must be something to do with these two other exercises, and the problem is this is quadratic, and this is quadratic, and that's quadratic, and nothing over here is really quadratic except 2x plus 5 squared is quadratic. And that's when I remember maybe I could factor these all into linear functions and to see what happens then. So I know how to factor each of these, and for those of you that can't remember how to factor, I suggest you go back on the channel and find some more of those uses or sort of those lessons on how to factor. Suffice it to say that if I factor the first and second terms in the numerator, that I get these factors, and if I factor the denominator out completely, I get all of these factors, which, if you looked at it closely enough, it's exactly the same as the exercise we just did. So if you looked at this, basically what I'm trying to do is, this is our goal for today, is to take complicated expressions like this use factoring to make them break down into their linear factors, and then divide out any common factors that remain. To get us to the point where we could do this, I'm trying to get you all to understand that since we know how to factor and we know how to do the exponent rules, we just combine them to make a new style of simplification exercise. Combine factoring with the division of common factors, and you get simplifying of rational expressions. First example has 27 divided by 27x plus 18. Now, to a student who's not thinking about mathematics, the first thing that they would want to do is cross out those 27s because canceling makes everything better. When we do that, we're going to get 1 over x plus 18. Now, it wouldn't take long to recognize how wrong this is, how these are not equal, but allow me to demonstrate with x equals 0. If x were equal to 0, the expression on the left would be 27 divided by 0 plus 18, 27 18ths, or 3 halves. So if I put in 0 for x here, I get 1 1/2. Put a 0 for x here, I get 1 over 18. They are not alike, no way. Let's look at a simpler example just to see and understand this. If I take x plus 3 over square root of x plus 3, so many students, they want to cancel the 3's because they're the same number, they cross out, they go away. But that's not right. It's not right for this reason. Let's take 5 plus 3 over 2 plus 3. A logical person would say 5 plus 3 is 8 and 2 plus 3 is 5, or 7, if I don't know how to add. Let's make that a 5. And then 8/5. But an irrational person would say, oh, the 3's are the same, so just cross them out, and that just gives you 5 halves. 5 halves is not the same as 8/5 no matter how you slice it. So basically, what I'm trying to say is when we use adding or subtracting in the numerators and denominators, the adding and subtracting are like glue. They're holding the two terms that are being added together, and they cannot be broken apart. No divorce here. So what we need to do, though, is we need to change this instead of addition. We should change it all into multiplication problems by factoring. So I look for common factors in the denominator. Oh, yeah, I forgot. Math crime. Everything I did in the above margin up here, all math crimes, and this is the stuff that you have to avoid. But I digress. Over here, we're going to look for common factors of 27 and 27x plus 18, which happens to be 9. 9 goes into both 27, and 9 goes into 27x, 9 goes into 18. So I take out a 9 from the denominator, and now I have something times something over something times something, just like we had a while ago right here. Same idea. So I'm going to divide the 9 by 9 and get 1. Instead of saying cancel, just say divide out to 1, and then we get 3 left over in the numerator and 3x plus 2 left over in the denominator. Looking at something even more complicated, here's a quadratic over a quadratic. All I have to do is break them up into linear factors, hope and pray that I get 2 of the same linear factors, which will divide out to 1. Notice my notation here. This is used sometimes. You can draw a line through each common factor and draw a little 1 there. So you're reminding yourself that they don't disappear. They divide to 1, and 1 times everything is everything. So we're going to take v minus 10 as a leftover factor, v minus 8 as another leftover factor, and of course, don't forget, you can check this. Here's how I checked electronically. I put in the given expression as an expression, and it gave me this graph. But as you can see, there is no red graph here, because I also put in my answer, v minus 10 over x minus 8, and that's what showed up here, is a little blue-purple. So basically, this expression gives you the same values as the expression above it, which means I did my work right.